Y'all back?
Oh, we are back. All right, right on. All
You can wait
right,
for
so what we're going to do is hook up our gauges, and we're going to get subcooled superheat. So let's head over here to our system. Can we measure our superheat right here? A way to measure superheat?
Without the clamp?
No, not without the clamp. We're going to use those two clamps.
Yeah.
Yeah, how did you do it?
On the suction line.
Is there a port for it?
There is not.
You can't.
So then no.
So you guys,
That's good.
I mean, you.
So he says we can't measure superheat. All right, what did you say?
What? Oh.
Did everyone agree with that? Why can't we measure our superheat from right here?
Because there's no access to the suction line.
Well, why do we need access to suction line?
So you got our saturation.
Temperature. We need to know our saturation. We got temperature.
Saturation temperature.
Oh, sorry, saturation temperature. Way to go, Charlie. Great. Well, we do have a port to our high side. So let's go ahead, hook up, and then press in the straighter, and let's get a subcool.
Let's go, Alex. The man of the hour. Go ahead, boy. You know how to do that.
That's
Wait, so this,
Pretend you're outside.
that's what line is that?
what, this one?
Mhm.
Liquid line?
Yeah, same as hooking up at the condenser then, right? Pressures are the same all the way through.
So I can, did you say the straighter's in?
Oh, this is a quarter presser, so it's not spraying right now
Oh, I can just put it in.
because I haven't tightened this down. So this is the same as a low loss fitting.
Oh, okay.
Everyone see what's happening here?
Oh, yeah, my bad.
What I was talking about, how new guys starting with manifold, I kind of like doing because they learn stuff like that. So you unhook right here. This is the one that connects to the gauge, which reads pressure. The other side is the one that has the dead end.
Yeah.
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 They're different on different manifolds.
Yeah,
but-
because I've only done the digital one, so I was confused.
Cool. Now, before I ever on a manifold gauge, before I ever hook up to pressure, I make sure my gauge is closed. And at 0, that's good. But these are closed, so clockwise is closed. So I'm double checking like this. If they're open, as soon as I get pressure, it's going to dump to the other hoses and maybe spray out. Close our gauge. Perfect.
It was anticlimactic.
Somebody else give me the subcool. We need what? Go ahead. Okay, clamp. I got it. What else? What else do we need?
There's no pressure on the gauge.
So our system's flat.
No, you have it.
Step in.
You gotta hold it.
Lean in. There you go.
Yeah.
Yeah. There we go. All right. We're getting closer. What else do we need? Adam knew, so he doesn't get the answer. Line temperature. That's exactly right. So let's get our line temperature. Just to make things interesting. We're going to climb onto our liquid line. Should I go here or here? Before or after the sight glass?
It shouldn't matter with the sight glass.
My guy, it does not matter. Man, put this guy in a van.
Yeah, look at
Too late.
At 3 p.m., put this guy in a van.
Get my baby back.
Okay? All right, we're getting closer, aren't we? All right, let's calculate subcool. All right, so let's talk some numbers here, okay? Subcool is the difference between the line temperature and saturation. Saturation happens inside the condenser before it's all the way liquid. Line temperature is after it's liquid. So we need our line temperature, one measurement. We need our saturation, And how far we come below that saturation is our line temperature. That gives us our subcool.
What's the saturation on it?
It was like so. Oh, 91.
91?
Yeah, yeah. So it is, no, that's not.
Okay? It's actually 93.
What number are you using for your line temperature?
The liquid.
Okay.
Well, you can't check saturation, right? Can we check saturation?
Yeah.
Oh, it's a suction line.
Yeah, yeah.
So
There you go. Nate, 2 degree subcool.
Yes.
Yeah. Well done.
Elliot, you get to keep
A little bit of experience would have told you that you're never gonna have a liquid line colder than outdoor temperature.
That's why I was like,
Because it's the outdoor that cools off the refrigerant. We never have a liquid line colder than outdoor, because the outdoor is what cools off the refrigerant. So I was holding it in here, it was colder, one labeled. But the point is, I want you doing the math. 91 is the line, 93 is the saturation. Is that refrigerant all the way liquid inside that line?
Yeah.
We've proved it by 3 degrees. It was all the way liquid when it was just 1 degree below saturation. And now it's 3 degrees below. We know it's all the way liquid. Nice. Great. All right, so the next one, Alex is gonna go outside. Alex, go outside, hook up to the suction.
Change your plans.
Just the suction?
We want superheat.
Okay.
We want
So you're
superheat.
coming with it?
Yeah.
So he's gonna go outside, hook up to the suction, and somebody's gonna call him on the phone and find out what we need to know in order to get our superheat.
We got a saturation of 40.
saturation of 40.
Right, perfect.
It's like
40?
it says 40.
40?
40 saturation?
Was it temp?
We don't
Good
know.
question. What is it?
Yeah,
Oh, we do know.
yeah, the saturation temperature is 40.
Do a little searching. Which one do you think is the right temperature?
49.
The one labeled line temperature, and it's liquid line, but
It's not.
we don't have it on the liquid line, do we?
No.
No, so it's 49.
It's 49, yeah. All right, what's our superheat?
9.
9. Very efficient coil. It's doing its job. We have come above the mixture state, 9 degrees. We know we're 100% vapor. You go above saturation, you're vapor. You go below saturation, you're liquid.
Yeah, I don't know. Cakes and French onion soup made their way onto the slide. But
Hungry.
yeah, I was hungry. The idea is there, though, that like if you're baking a cake and you put it in the oven, right, you usually have a blower on your oven if you want something to cook faster, right? If you circulate the air, right, you're moving the heat and you're getting more efficient cooking. The same thing is my French onion soup example was if I have a spoonful of soup, right, and I'm gonna put the hot soup in my mouth, what am I gonna do before I put it in my mouth? Blow on it, exactly. I'm gonna cool it faster by moving air across it, right? We're getting better heat transfer by moving the air. Same idea is with my blower motor, right? I'm getting better heat. I could put an evaporator coil and have it just sit there,
In
right?
the room, you could hang it,
Right,
a fixture.
it'd be great, it'd look
It'd be
cool.
really cold.
But it wouldn't really cool the room though, because I'm not moving air across it, it's just sitting there, like an awesome chandelier. So we need to pass the air across the evaporator coil in order to get the heat out of it, right? I need it moving, that's the blower's job,
I
it,
kinda want that chandelier now.
right?
The
Okay.
evaporator coil, forming ice, yeah,
I think it could double as a disco ball.
kinda want this.
So we need the coil to have as much contact with the air for efficient heat transfer. When you're looking outside, the condenser coil, right? We said that a clogged or dirty coil isn't gonna let air pass through it, right? Because we've clogged those fins with dirt and dust. Same thing on the inside. If I'm clogged with dust, with dirt, with hair, with whatever, pet fur, then I'm not getting air through my coil. Those little fins serve a purpose. The more, so aside from looking cool, they are all, if I just had straight copper pipe running through the evaporator coil, it would work. But the more surface area I can put in contact with the air, the better the heat transfer I'm gonna have, right? So that's why the manufacturer will put those bunch of little fins all over the thing. It's because they're trying to create more surface area in contact with the air to get better heat transfer across the coil, right? The
They're
fan-
also created, if you look at them really closely, you notice they're going like this.
Oh, yeah.
And so those thin metal fins are like, they're not perfectly straight. That way, when the air is moving through, the air is forced to smash into each side. It's creating turbulence. So even more of the molecules of the air and the moisture in the air are making contact with the metal surfaces.
So the fan speed is also an important part of this. If you guys have seen those, the motors inside the air handlers, right, they've got multiple speed taps. Furnaces are a little different, you have less options, and then there's the variable speed ones which decide what speed they want to run on their own. They don't care what you say. But the speed taps, you can set the speed of the blower, and you'll see that reflected in the pressure. If I have too much airflow, I'm going to see a higher suction pressure. If I have not enough airflow, I'm going to have a lower suction pressure. So generally, when we do installs, we like to set speed 2 on your normal ECM motor for cooling, and we like the 4 for the heating mode, because you want more airflow when you're heating than when you're cooling. When you're cooling, I want lower airflow, yes.
No, I was just gonna ask on the thing with the ECM, is that just a thermostat programming thing?
No, it's the
Okay.
thermostat just tells the fan run or don't run. What's controlling that is either a board if you have a certain kind of air handler, or the actual speed tap you put onto the motor. It'll have like speed taps 1, 2, 3, 4, 5, and wherever you put your G call is where that motor will run.
Oh, okay. So you just whatever. You probably usually as a installer, you're like looking at like what is the specific speed they need and.
Yeah, exactly. So we're trying to hit a certain CFM. In Florida, sorry, in the rest of the country, in most parts of the country, they're usually trying to hit 400 CFM, which is cubic feet per minute, like how much volume of air we're moving across. In Florida, we actually go lower. Our target CFM for this market is 350.
Per ton?
Yeah, 350 per ton, exactly. So for a 2-ton system, I would want a CFM of 700. For a 3-ton, it'd be 1050. But most of the time they'll give it to you, the manual will give it to you either in CFM per ton, or they'll just give you the flat number and you can calculate it based on the tonnage of your system. The reason we want it lower though is because of this.
We touch humidity.
Do it?
Is it the humidity?
Exactly, exactly. So we talked a little bit earlier, we got sidetracked talking about sensible and latent heat loads, right? I have water in the air. Some of the heat that my refrigerant absorbing is going into taking latent heat from the water in the air to condense it, right? So I won't see as much of a sensible temperature difference in the air if I have high humidity. That's why when I'm calculating a target temp split, I'm looking at at the humidity in the air. If I have a high humidity, I'm not going to hit a perfect 20-degree temp split because some of the heat that I'm absorbing is actually condensing the water into my coil. So humidity does play a huge factor. It's also why we run our fan speeds lower. We're trying to not just cool the air, we also want to dehumidify because that plays a huge role in comfort, right? So if I have a room, and let's say, and you'll see this a lot of times during the winter, right? The room might be 72 degrees, but if my humidity is 70 degrees, it still feels sticky and nasty in there, right? Because I've got high humidity. So I want to dehumidify because it feels more comfortable to the customer. Usually we set our target humidity on like 54% or so. So by running our fan speed lower, letting that air hang out over the coil a little bit longer, we're getting more humidity out of the air, and we're hitting our target temp splits. So in Florida, your target CFM is about 350 per ton. You can play with that depending on the system, but that's the basic idea. We're trying to dehumidify much more than other markets because for our comfort, that's a huge factor. What else did I hit here? Yeah, 350 CFM is our target. So temperature split. So your target temperature split is going to vary a lot. 20 is ideal. I think I put what I put on there, 16 to 22. you can calculate, so there's a calculator in the HVAC school app where you can actually give it some numbers. It's gonna ask for your return temperature dry bulb, your return temperature wet bulb, and your outdoor ambient. And you plug in those values and it'll spit out a target delta T and also a target superheat for charging a piston system, because they're related. If you're not sure, if you're reading like a poor temp split and you don't know if you actually have a problem or not, throw a quick calculation in there, because a lot of times relative humidity will play a factor in what you're seeing, and it doesn't have to be 20. But what we're looking at, where we're putting our probes is we've got one in the return, measuring return air, we've got one in the supply, measuring the supply air, and we're looking at what is the actual sensible temperature difference between these two things. How efficiently is our system cooling the air? Return and supply, yep, and those psychrometers will measure the humidity and they'll measure the dry bulb temperature as well. So they can give you all the numbers you need, and you just have to figure out whatever the outdoor temperature is. I usually just look at the weather, but that'll get you close enough to see.
Yeah, that's been working for me.
Yeah.
I've seen that.
It's usually pretty good. So this is one of the 5 pillars. This is one of the things that we'll look at that can help us determine if we have a low charge or if we have an airflow problem. You don't want to go, I think we touched on earlier, you don't want your temp split to be too high. If I have a high temp split, it's usually because my air is hanging out over my coil too long, which means I have an airflow problem. I'm either restricted, or I have a poor fan speed, or I have a dead blower motor, or something's going on that's letting my air get way too cold in there. My coil will freeze over eventually. And then the other way, it just means I'm not cooling efficiently.
With a high temp split?
Yeah, the high temp split is, that's usually, that's an airflow restriction. A lot of times, and I don't know, if we might get to this later, but where your symptoms about airflow, you'll see that high, the low superheat, right? Because I am boiling refrigerant throughout my coil all the way, and I'm not picking up anything extra, no extra sensible heat. I've also got a really high temp split because my air is just sitting there, it ain't moving. So the longer the air sits there, the colder it's gonna get, and I'm gonna get a crazy temp split between my return and my supply. So yeah, it's important. I'm not gonna say it's not as important as the head pressure, suction pressure, superheat, subcool, but it is a factor. A lot of techs won't look at this, but it can help you pinpoint some of those more difficult diagnoses. We'll briefly talk about static pressure. This isn't something that we normally measure. This is not one of my 5 pillars, but it is something to know. The ductwork does play a factor. One of the other problems you can have with airflow restrictions isn't just the filter of the coil. You can have issues with your ductwork that are causing poor airflow. You have restrictions from a crushed duct. You have a crushed return. It's not letting the system breathe. Something's happening, and you might not be able to see that visually, but you could if you used your manometers. You would see a high static pressure. Static pressure, basically the same way we're measuring refrigerant pressure in the pipes. We're measuring the pressure of the air on the ductwork itself. That's what our manometer is telling us. And we won't get into how to measure it, but it is a thing. Just be aware it exists. And then we already talked about outdoor airflow, about what happens when we have a dirty coil. If I can't, for the same reason, if I can't move airflow here and it's getting too cold, outside I'm gonna have the opposite problem. No airflow means it's gonna get really hot in there. You'll see the same problem if my outdoor fan motor dies. You'll watch your head pressure go through the roof because I'm no longer rejecting heat. It's just sitting there and heating up my compressor. Eventually my compressor will go out on thermal overload. But yeah, so you want to keep those coils clean. It improves efficiency and it just keeps our pressures down so everything runs properly. We're only touching this briefly before we go do some more hands-on stuff. Does anybody want to know anything else about airflow right now? I know we hit it briefly.
Can airflow change your superheat?
Yes.
Can it change your suction pressure?
Yes.
Can it change your head pressure?
Yeah.
Yes.
Can it affect your subcool?
Yes.
Yeah. If it-
Okay. They're all right, except for the one no I heard? Absolutely. Every bit of the refrigerant circuit can be affected by that.
Yep.
But airflow.
Yeah.
We're gonna answer these questions real quick with the information he just gave you. The refrigerant circuit, our combined knowledge, and some of our combined experience. 3 most common causes of low suction pressure.
Low charge.
Low charge.
I'll take it.
Manny, what does low charge mean? Cheer! Exactly, see? Understand, when you guys are training other people, when it's your turn, or when they're training you, there's a language to learn in the trade. If you said low refrigerant, he would have figured out what you meant immediately. Same thing. Low charge is the low level. If somebody has added refrigerant and they set it at a low charge.
Yeah, because in my head, I went to the controls in the outside unit that will have an actual electrical short, so I wouldn't have.
Electrical, no. Low charge. So, is exactly right. Here we go, common causes. Low charge is one of the three most common. I didn't write down the words most common, but I want the three most common. Alright, so low charge is one of the three things that can create low suction pressure. What is low suction pressure? It's the low pressure read from our suction line. Low suction pressure means low saturation as well. Yeah, or just low. Cool. Could be freezing, could be that low. Alright,
You got
next.
I was gonna say real quick, low is relative, some of that's gonna come with experience, but this is where we use that rule of thumb, where we're taking our return air temperature and we're checking to see, are we 35 degrees below on our saturation?
Yeah.
So anything that's below that is what we mean by low, because just because the number itself is low doesn't mean you have a problem if you're working with a different kind of refrigerant.
That's
If it's cold in that room already.
It's cold, yeah.
Dirty filter.
Dirty filter, okay. I'm not gonna write dirty filter because we want a more broad description in that third, but the dirty filter is one of the parts of that, yeah.
Low airflow.
Low airflow. There we go. Low airflow. And causes of low airflow, guys.
Dirty filter.
Dirty coil, dirty filter.
blower not working, whatever.
Failed blower motor.
And, another one that is kind of subtle, but fits in the low airflow category for just this discussion, is when the house is really cold. Maybe the same amount of airflow is moving, but there's not nearly as much heat in that air. A better way of doing this would be low load on the coil.
Yeah, Don said it, he said
Yeah.
low heat load.
Which is, we use our air to bring the load to it. So 90% of the time, low load means low airflow. But I'm cool with low airflow. Dirty evaporator, dirty blower wheel, blower speed set to the wrong speed, failing blower motor, clogged filters, panel insulation pulling in, blocking stuff, piece of furniture put against the return, 2 filters in the system when there should only be 1.
Pressure ductwork.
Crushed ductwork, undersized ductwork. Low airflow. Now, before I move to the third one, how in the heck does low airflow create low suction?
That's what
I mean, think about that. We got our pressure drop happening right here. The metering device is controlling our pressure drop. Our compressor is pumping it. Those two things don't change their function.
Can we see the suction line temperature, 48 degrees? Alright, watch this. What's happening to my suction temperature?
Drop it.
Whoa, what are we at now?
Yeah, 38.
What'd I do?
You took it
Added more air.
No?
Less pressure, I mean, because it's open. More space.
We did not add more air to the coil though.
This didn't increase the heat load. I opened a sealed system, right? So now,
And then going over.
well, the fan is still pulling air over the coil.
It sucks.
Yeah.
With less pressure?
Because it's taking in this.
Taking in this air.
Yep.
Before, all the air was forced through that coil.
Straight.
Now, a big part of the air that the blower can move is going around it. So that means that we
All
have
this is open.
less air making contact with the surfaces of our coil. That air holds heat. That heat would be normally transferred into that line, that suction line, and come out here. But it's not being transferred into that line as efficiently. And so now our suction
33 degrees,
33.
37 degrees, we're almost freezing on the suction line right now.
Do you know what's happening outside to our suction pressure? What did we learn about temperature and pressure?
It goes up, doesn't goes up. It goes
Yeah.
down the other way.
They correlate. Exactly.
So if it's 33 degrees, it's my sensible temperature.
That means pressure
Right.
is dropping, so.
Yeah, my pressure outside would be really low. It'd be around like, it's less than 100 right now.
Yep.
And
And on its way down, the problem is compounding. As there's less airflow, the coil's getting colder. As the coil's getting colder, there's pressure's going down. As the pressure's going down, the temperature's going down. As the temperature's going down, they're compounding.
And once it starts to freeze, it's really gonna ramp up, because as it freezes, that ice is not gonna block any
Ramp down.
airflow you did have.
Is that what you're saying?
Yeah, well, this, yeah, and we, this is, well, it was already condensating, but watch, when this gets below 32, we're gonna start seeing frost form here. If I leave this off, this will frost over. As it starts to frost over, I've increased my airflow even more, right? Exactly. So a lot of the time, when you see it pull up to a system that's frozen, if you don't get there in time, right, it's like that coil will just be a solid block of ice. It will continue to freeze.
Because the problem is keeping it wet.
Yep.
So, this is how low airflow, which is the lowering the amount of heat that's coming into that coil and into that refrigerant, brings the refrigerant pressure down. So part of what gauges the pressure, metering device, and the compressor working together. But another part of what sets our pressure is that balance point of how much heat are we putting into it. If we're not putting heat into it, then the pressure will continually drop as it gets colder and colder, because cold temperature creates lower pressure, and lower pressure creates colder temperature. If you run into a problem, you show up on a system, you look up your gauges, and we got very low suction pressure. You can immediately find out right there if the issue is low refrigerant or airflow by just grabbing that suction line. Is the suction line icy cold? The issue is airflow. I have plenty of refrigerant to get that coil cold, but I don't have enough airflow. Or if you grab that suction line and it's warm with low pressure, then you know we're starving our evaporator. We're not putting nearly enough liquid refrigerant into our evaporator. I do get that new guy call. Charlie didn't call me with it, unfortunately, but I get that new guy call. Almost everybody who goes into a van at one point calls me freaking out about their pressures. And I say, you should walk upstairs and put those panels back on. Oh, that's right, I forgot I was cleaning the drain. What was that? You guys just all got COVID.
Now the coil will freeze even if it has low charge, because it's below freezing. If it's still got enough charge in it to like cool a little bit, it'll freeze the coil even though you've still got good airflow. So on that one, a good, and this is an experience thing also, is like if you come up to a system and the coil's frozen and you go outside and the compressor's frozen too, like there's ice all over your suction line, you've got an airflow problem, because you have enough refrigerant that you've been evaporating all the way outside. If you have a frozen coil and you go outside and you don't have ice all over your suction line too, you probably got a charge problem. Yeah.
All right, that brings us to number 3. What is the third most common reason we come up and we find low suction pressure? Now, Adam has got us both of the first two. Anybody else want to guess the third?
You have like restrictions in the metering device.
It's my guy. So to make it simple, we're going to do bad. T, X, E.
We should say that.
Oh, we're not going to. We're not going to get technical here. I'm doing this to make everybody online watching this video upset. We have a bad TXV. That is the third most common reason. The TXV is located in the liquid line, so sometimes people just call that a liquid line restriction.
Yeah, like me.
Like Elliot. However, 9 out of 10 times it is the TXV when it is a restriction in the liquid line. So we're gonna just call this a bad TXV. How does a TXV create low suction pressure? Name. A bad TXV.
There's not as much in as the coil.
That's right. It's not letting as much go into the coil. So if it's closing down, then our whole low side, which is being fed through this, is being fed less. A bad TXV and low charge look identical on your low side. You guys got that? Bad TXV and low charge both have low suction pressure. Because we don't have very much liquid coming in, it's boiling off really fast and creating a really high superheat. So it has low suction pressure. We're also bringing our suction saturation down, so we're creating a bigger difference between saturation and the heat.
So high superheat.
High superheat. Low suction, high superheat for 1 and 3. Both of them exactly the same. Low suction, high superheat. How in the world would you be able to identify which was actually the cause by taking more measurements of the system? Well, whether it was low charge or bad TXV that's restricting it, causing our low suction. Now we need to take more measurements of the system, use our 5 pillars. Okay, subcool. What will subcool tell us?
That you have enough refrigerant, just like if your subcool's good, you got enough refrigerant, it's just your TXV.
That's right. We learned earlier, if our subcool is good, high, if our subcool is fine, our refrigerant level is fine. So regardless of what we see on that suction, if our subcool is good, we don't need to add charge. That's not what our problem is. So we've now identified the difference between, we can now diagnose a bad TXV versus low charge. Right there. Both have low pressure, high superheat, only one has good subcool. The bad TXV has good subcool because it's restricted here, but it's still backing up. Nice high pressure, plenty of refrigerant in here. So we're still doing our job over here on this side. It's this side that's restricted and dropped down and not doing its job. Now, low refrigerant. What are we gonna notice when we hook up on our high side and we have low refrigerant charge?
It's fighting me.
It is so like right there.
No, I meant like I started to do it and the TXV's fighting me. It started beating.
No, it's trying to.
Well, it started,
yeah.
I got it up and then it adjusted itself.
It adjusted.
And there we go. Now I'm starting it now.
That's pretty cool.
Yeah. So.
We could hook up the rest of the probes if we wanna.
I could.
We'll get you out of your seats before the rest of this.
Sorry, yeah. I'm
Yeah.
playing it right now.
Well, we are gonna.
But you can see, so I've created a liquid line restriction, not necessarily a bad TXV. And I've got, where'd it go?
I'm trying to give you the actual.
Gotcha.
Oh, I'm sorry. All you can see is the line temperatures anyway, huh?
Yeah, no, so I've got my, you can see how my section line is starting to climb and climb and climb. If we looked at the pressure, what we would actually see was that the pressure is low, so I have a high superheat right now because I'm starving my coil of refrigerant. So you'll watch the section line.
Still the same amount of heat coming into that coil with airflow, but now less refrigerant. So the heat is boiling quicker and bringing that temperature up higher, higher superheat. High superheat means we don't have an airflow problem.
And if you
We
were
can
watching,
just check that off the list.
see, if you were watching earlier when I first started to do it, what happened was I started to get that number up and then it started to come back down because the TXV tries to maintain a constant superheat. So the metering device actually adjusted for the flow that I gave it to try and maintain that constant superheat.
So let's answer that question. If we have low charge, we already know our suction's low, our superheat's high. What is it gonna be like on our head side?
High pressure. I didn't know low pressure.
We'll have a high pressure, okay? He says low. What do you mean by low though? Low's relative. You don't have to guess a number. Low compared to where it should be maybe?
It probably was the average number.
Okay, an average, okay. if we use his rule of thumb, it would be low compared to that, what was it, 12 to 15? Yeah, it'd be low, the saturation. But what's the easiest indicator? We just used it on our TXV. Yeah, that's right, subcool. Subcool is the easiest way to prove that we have low charge. Because if you remember, low subcool means we have a low amount of refrigerant there. Good subcool, high amount of refrigerant. So we're checking our subcool. We don't actually have enough refrigerant to stack up against here and hang out in the coil long enough to come into a liquid and then drop even lower in temperature below the liquid. It's coming out of there still, sometimes zero subcool, still partly saturated, but all you need to take away from that is low subcool, low refrigerant. If both sides are giving you low refrigerant signals, you're low in refrigerant. If your low side is giving you the low refrigerant, but your high side is great, you have a restriction. Yeah. All right. Now, airflow. Low airflow. What is going to be the difference between my low airflow and my low charge? They share a very distinctive difference on the low side. So let's say we don't have anything to hook up to the high right now. Only have a low, and we got to find the difference between these three, or between airflow and these two.
How quick you're boiling?
Okay, it is how quick your boiling changes. But we can't ask a system how quick its boiling changes. We have to do a test that tells us how quick the boiling changes. What is that test called? Think about what Elliot did. He just created low airflow, right? When he took the panels off?
No,
What happened?
it's like airflow.
Your saturation drop?
Your saturation drop, which will be low suction pressure. So we already know all three of these have that, sure. But low charge and bad TXV have something that airflow does not.
Superheat?
Yep, it is superheat. What is it?
Superheat or zero?
Low or zero superheat. If you have a cold suction line, remember that's what happened immediately when you opened it? Cold suction line. You're gonna have really low superheat. If it's bad airflow, it's not picking up as much heat. Low superheat. If it's being starved or low on charge, you're still picking up plenty of heat.
What is this?
High superheat.
Okay.
So low airflow, low superheat, cold suction line. I had said earlier when his panels are off, if you walk up and your gauges show you really low pressure and you grab the suction and it's icy cold, it's not low charge. You have low airflow. Yeah. But if you grab that suction and it's hot or warmish, it's not as cold as it should be, then for some reason we're not getting enough refrigerant into the coil. So, cold line, warm suction line. In low airflow and bad TXV, you're gonna have a normal, pretty good subcool. Only in low charge will you have your low subcool. So again, the subcool, indication of charge, and then suction line temperature, indication of airflow versus refrigerant.
So I just Googled 5 pillars of refrigeration, and this chart comes up, it's on the HVAC school. I've seen laminated copies of this in some of the vans. But this is a really good tool when if you are just starting out and you're trying to do a diagnostic. This chart has stuff for, it has fixed metering, but this is the one for the TXVs that we use, and it's got, these are the 5 pillars, right? I got suction, I got head, I got superheat, subcool. I really don't care about compressor amps, but I do care about my delta T. And this is what Bert's talking about, is a lot of these look similar, but there's key differences. So the difference between a low charge and a liquid line restriction, right? The difference between low airflow and a low charge. You're gonna see some key indicators that tell you what the problem is. So this is a good reference chart if you look that up, or you look for that in HVAC school.
Again, if you continue with revisiting the fundamental knowledge, what goes on here, and connecting it to what you're seeing in the field, all of a sudden, without having to do a lot of process without looking up a chart, you're gonna be able to put it together. You're gonna put a clamp on that suction line, it's gonna be cold. And then immediately you're gonna be like, okay, I know I'm not getting the heat load that my coil needs, but I know I'm getting plenty of refrigerant because it's cold. But I'm not picking up enough heat in the coil. Gotta start looking at airflow stuff. Yeah. And so the depth of your knowledge here really helps translate to diagnostic issues. Which brings us to the next one, two most common causes of high head pressure. Head pressure is our liquid pressure, is our condenser pressure, it's this whole side. Overcharge. I heard that.
Because low airflow for that one too.
Yes, it is.
It is.
Yeah.
It's pretty.
Which is the same thing.
Both ways, yeah.
Yeah.
Right? Dirty condenser, same thing as low airflow. So low airflow means it's not rejecting as much heat. We know that if it doesn't get rid of its heat, then that high temperature creates high pressure. So we're gonna have a higher pressure. We're gonna have a high head, higher than normal. We're not getting rid of our heat. We're dealing with higher temperatures, right? But at the same time, we could have overcharge happening, but it's not because of low airflow. It's not because of really hot coils. We've added too much refrigerant. So how could we test to find out the difference between which of those two is causing the problem?
I mean, the overcharge.
I was gonna say maybe for the overcharge, I mean, we know we look at subcool for refrigerants.
Yeah, overcharge, really high subcool. If it's just low air, your subcool stays close to the same, just all your temperatures go up. Higher liquid line temperature, higher saturation, but they still stay pretty close to the same. If anything, once it gets bad, it gets lower subcool. But overcharge, you're gonna have very high subcool. And a much easier way of actually doing this would be the same test with low airflow. Over here, if our suction line's cold, we have low airflow. Well, if our liquid line is really hot, we didn't get rid of heat via the air like we were supposed to. So if our liquid line is a lot hotter than the outside air,
Stay trapped in the refrigerator.
yeah, somehow that heat stayed trapped in the refrigerant. We didn't get rid of it. We don't have enough airflow cooling that refrigerant down. So it's one of the easiest things to do to see if your coil is efficient is take a temperature. You can just grab the line. That's pretty hot liquid line, holy cow. Very inefficient condenser coil. What do we got going on here? So let's give this thing a wash. It might look perfect, but it's probably internally packed. And so if it's not getting rid of its heat, we're gonna have a higher temperature. If it's not picking up its heat because of airflow, we're gonna have a colder temperature. Airflow is discovered by temperatures. Refrigerant charge is discovered by subcool. All right, that was a lot.
Yeah.
I think that covers all of our slides.
Yeah, I'm done.
Yeah.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.